Okay, so welcome everyone to the last day of this workshop. Okay, so today is going to be about dynamic algorithm, why length constraint expanders are useful in dynamic algorithms. So it's about robustness of expanders. Okay, so I will give like the first part of the talk, and then my student Yahweh will explain the details. And so let's begin with one concrete problem, which is dynamic distance oracles, right? Like think of Google Map or something. That is, you have an undirected weighted graph. Weights might you think of it as a traffic, but then there is a sequence of updates given to you, can be edge insertion or edge deletion, and then you just get a query. At any time you have a sequence of update. At any time step, you get a query, U and V, and you ask you need to return what is the approximate distance between U and V. Okay. So the goal is usually just to minimize the update time per update. Given one edge update, you update your data structure fast, and you should have fast query time, something like log n or subpolynomial. In our case, we get something like log n even. So this is one of the most extensive study in dynamic graph algorithms. And there are really a lot of works like here and here. And yeah, in the next 2 hours, we're gonna basically study this table in details. Of course, I'm kidding. Let me summarize the state of the art for you. So the idea, basically when we think of fast update time, by fast I mean n to the epsilon update time, it turned out that there are some fundamental barrier in the state of the art. That is, all known fully dynamic algorithm. By fully dynamic, I mean it can handle both both insertion and deletion. All these algorithms, they all have only amortized update time, even if you allow bad approximation like almost n approximation. Also, another barrier is all fully dynamic algorithm that is deterministic. They all need quite big approximation ratio, polylog. So in more details, like the goal, one of the research program actually kind of start from the work of Chechik, where she show dynamic distance oracle such that the approximation ratio, the trade-off of her approximation ratio and update time really is optimal. But when you allow this update time, it's just constant, but her approximation ratio is optimal. However, there are some other drawback, like her data structure is not fully dynamic. It can only handle in deletion. It's also randomized, and more importantly, it assumes oblivious adversary, which means that it cannot be used inside other static algorithm. Also, it has amortized update time. But because her work is optimal in the trade-off of approximation and update time, this kind of set the research program. Can we match her bound, but remove all this drawback? It turns out that in the insertion-only setting, which is usually much easier, one can kind of do it. We can get constant approximation, deterministic, and worst case. But that's for insertion only. Okay, then there is a work that shows by Foster et al. They show that, okay, in the fully dynamic setting, they can handle updates and get good approximation too, but still have bad, have randomized only guarantee and also only guarantee amortized update time, and it's randomized. Okay, and then there was a breakthrough by Chusoy and Zhang. Here, they managed to get deterministic algorithm now. It's fully dynamic too, but the approximation is still quite big and it's amortized. So the point is, again, all of the non-fully dynamic, or even if you need to handle deletion only, you have only amortized update time. And for deterministic algorithm that is fully dynamic, it has a big update time, big amortize, big approximation ratio, sorry. Then there was a work that is presented before, like that is published before us, but independently by Rasmus, Simon, and Max. Here they show that they can get fully dynamic, deterministic, and worst case, but with a big approximation, but they have some nice other nice property. Now what we show is that basically now we can get everything, except that, okay, the approximation ratio of constant here is not the optimal constant, but at least we can have almost reached the goal. And because this is deterministic, it has a good application because we can use this as a data structure inside other static algorithm. And what we get, for example, is constant approximation for multi-commodity flow in almost linear time. But here we get it for vertex capacity setting. Yesterday we saw how to get it for edge capacity setting. The techniques there doesn't work for vertex capacity yet. With this data structure, you can make it work for vertex capacity. So there's something nice going on. And we want to tell you like what is behind this development. And our approach in a nutshell is to make this object low step flow emulator, which is like one of the key objects throughout this workshop to work in the dynamic setting. Just to stress the lesson throughout this workshop, okay? You see that here, even if you care about distance only, it's dynamic distance oracle problem. It turns out that the fact that we can control congestion using this flow emulator, this joint control of congestion and length, it turns out to be useful. The fact that you can control congestion is good in the dynamic setting, and you will see how. And let me recall a bit, just very high level, what is low step flow emulator, right? Low step flow emulator is something that you build from length constraint expanded hierarchy, which is just the length constraint expander decomposition on top of each other. In picture, it looks like this. You have some terminal set, you find some cut, like some length increase, and you build the width of expansion, which is like a router on top of vertices. And then you get this expanded decomposition for one level. The cut edges induce a node weighting, the terminal set in the next level. And you try to compute expanded decomposition in the next level. And maybe it looks like this and you're finished. So the main question is that, okay, this is like some structure that looks good, but can we dynamize it? Can we really maintain this kind of structure in the dynamic setting? That's the main question today. And my goal is that at least the first thing that I hope you to get is that you should have a clear intuition, at least why expander and length constraint expander are just intuitively robust under update. So it's like, once you see this, you can have like a hope that, okay, this should work in dynamic setting. But then you should realize that there are some challenge when you want to maintain expander decomposition on top of each other. The challenge is in maintaining the hierarchy. There are some care you need to take care of. And then you learn how do we overcome these challenges. So the focus here is not about dynamic distance oracle itself, but I hope you to see how to dynamize this core structure with should be some promising future application. So before we talk about our work, I want to shout out for other works too. That is, for example, the work by Rasmus, Simon, and Max. This one that is independent from ours. Here they do something very interesting, which is they dynamize something called low step distance emulator by Adoni, Stein, and Jong, which is obviously related to low step flow emulator. It's not clear to me yet, actually, how these two are related. Can we get a common generalization of both work? There's something very interesting going on. Also, the work here by Chusa and Zhang, right? There is something very interesting too. In fact, they are the first deterministic algorithm that breaks the log-n approximation barrier that usually is there when you use only normal expander. That breaks it to polylog-log approximation. And to do that, they need to introduce some new technology too. They introduce something called well-connected graph, which is related to length constant expander. They introduce something called length distance matching game, which is related to cut matching game for length constant expander. They also have some version of dynamic router, but they are which we will define, but their version is has amortized update time. So there are really some connection here, and we hope to understand this more. And I hope that once we understand all this works, there might be some unified framework that give you common strengthening of everything. Okay. But for today, we talk about our work. And the setting that you should have in mind, the model of how the graph change, we'll look at the simplified setting, which I call for today is called is one batch update setting. So what is this setting? So it's a setting where you you're just given one graph, then you try to pre-process this graph. Let's say in almost linear time. And then there is a single batch of updates. Just a single set pi of edge update consists of saying which edge you want to delete, which edge you want to insert. They all come in one go. And you just need to handle this update in one go. It's not like a online sequence. Okay? There is a single batch of update. Then you just update your data structure. You should try to update this data structure in time that is basically almost linear in the size of the batch. Okay? And after that, there is no update anymore. You just need to answer the queries. So it's an easier setting that is simpler. But I want to note though that this simple setting already almost captured the hardness of everything. So it's a good model to think about. Why? Because of this theorem, which says that suppose instead that you have something similar to this setting, a single batch. Instead, you are given B batch of update, and B is a constant. Okay? A batch 1 up to batch B. And if there exists a B batch algorithm such that on the ith batch, you spend time that is almost linear in the size of the ith batch. Let's say the size of the batch times into the epsilon. Right? Then there is a black box reduction which says that immediately you can just use this and you can devise another dynamic algorithm that can handle a sequence of edge update indefinitely, such that the worst case update time is basically into the epsilon. And note that here you get worst case update time, not amortized. So the takeaway is if you want to think about dynamic data structure with worst case update time, I would encourage you to just think about this simple setting, one batch setting. And this is a setting that we're going to present today too. Okay. Okay, so now I want to give you intuition why expander are robust. So let's start with this intuition. Let's start with just normal expander, right? So when the graph is not an expander, it means that there exists some sparse cut. Yeah, there can be two big components connected by few edges, like two edges in this picture. But you can see that if there is a sparse cut, and let's say I delete these two edges, then how connected components of the graph change? They change in a big way. You start with one component, and then you just delete two edges, you get two big components. That's a big change. Intuitively, it's bad. On the other hand, if the graph is an expander, right? For any cut, there are like, if the graph is an expander, if you look at this graph, if you look at the balance cut, if you delete this just two edges, you know that there are still a lot of edges crossing the cut because the cut is balanced. These two edges will not change anything. And if you delete, let's say k edges, yeah, in expander, you will be able to just disconnect something like volume of k from the graph. So after k deletion or k update, you can disconnect, you change the structure of the graph by volume of k. So that's why it's intuitive that small update gives you small change, and that's intuitively good. And here is the theorem that basically formalizes intuition in a really strong way. It's called expander pruning. So it says the following. If you start with a graph, which is a phi expander, then imagine that there is a sequence of edge update given to you. Then there is an algorithm that maintains some vertex set P, such that the vertex set P will grow slowly and the update time of this set P is small. And what is the guarantee about this set P? It says this. Okay, imagine that you have a graph here. In the beginning is expander, then you delete some edge. Then the algorithm will grow a set P, P1. In the beginning, it's small, right? And then the guarantee is that at any time, the complement of P is still a 5/6 expander. So the complement of P here is almost as good an expander as in the beginning. The next update comes, then the algorithm update your set, and the complement here is still an expander, and so on. So the set P is updated, but it grows slowly. The size of the P, the volume of the P here, after I update, is something like I over 5. And the update time to update P is also small per update. So that's what's happening. You can see that one update really is just affecting expander in a minimal way. Each update only causes small problem. The set P, think of it as a problem set that you try to prune out. And the remaining part remain expander, a good one, a robust one, right? So this really formalized the intuition that we give in the beginning. So this is why expander are just robust over edge update. What about length constraint expanders? So let's recall a bit, right? What is the structure of length constraint expander? Let's look at the width of length constraint expansion. So what do we have? Suppose that the set A is length constraint expanding. It means that there is some neighborhood cover of a graph such that for each cluster here of the neighborhood cover, you have some router on top of it, router that connect to everything in A here, right? And then there is an embedding that embed all this router into the graph G with small length and congestion. So the thing is that it's really the router that kind of on top of everything. And the point is I want to make is that router are robust under update too. And if the router are robust, then the embedding should be robust too, because the embedding just correspond to the router. Why is it the case that routers are robust under update? Morally, it's just because the way you should think about router are just dense expander. Okay. We see some example in the workshop that if you think of two-step router, one way to implement two-step router is just a click. It's a dense expander. It's maximally dense. If you relax the number of steps from 2 to some like larger constant, like 1/epsilon, a way to implement this is to start with a hypercube and look at the power of this hypercube. So start with the hypercube, and anything that is within the range of epsilon log n, connect it to make it the neighbor. That's the power of hypercube, and the degree is going to be denser, not just log n, but n to the epsilon. But you basically start with an expander and you make it denser. So router, just think of it as a dense. And you know that expander are robust, so router are robust too. So of course, like robustness of routers alone is not the only thing that we need to care that matter and make everything dynamic. But there are, at least you see that the key object on top of this witness of length constraint expansion, they are robust. So we have hope. So now I want to point out the challenge. Okay, we have a good, like intuitively, everything should be fine. What is the challenge? Okay, so the challenge is in the hierarchy. So let's again talk about normal expander case first, and then I point out the challenge, like the even bigger challenge in length constraint setting. So to talk about expander hierarchy, we need to recall expander decomposition. In the normal setting, it looks like this. You have a graph and some parameter file. Then it is a partition, right? It basically you cut something. The amount of thing that you cut is something like five fraction of edges. And in each part here, you get a phi expander. So it's a partition of vertex set into induced expander, and the amount of thing that you cut is 5 fraction. So by now, this picture should be, this mental image should be clear to you that for any graph, every graph is just a bunch of disjoint expander plus small fraction of edges. Okay, from expander decomposition, the way to construct expander hierarchy, one way to construct it is like this. Start with the graph, compute the decomposition, which partition the graph into parts, contract each part into a vertex. The red edges here become the red edges here. And then you decompose again on the contracted graph and contract and repeat, right? Until you get one node. Okay. And once you are done, then you can see that this kind of induce a tree structure just by connecting the vertices in the natural way. If this node is contracted into this cluster, then you connect them. So you get some tree structure, some hierarchical structure like this, where in the bottom you get the bottom here is just a original vertices of the graph. Okay. So we have this structure. How do we dynamize it, right? There are actually two main tasks in our approach that enable us to dynamize this structure. The first is that you have graph size reduction per level. I tell you more about this, but the point is contraction is crucial in some way. The second is that you need to control the recourse between levels. We need to take care of these two things just to get fast dynamic algorithm for maintaining expanded hierarchy. So let me talk more about each of these two. So first, graph size reduction per level. Why do we need this? So I want to say that there are two very different utilities of contraction. Like when we construct this, you contract the expander into one node. So the first utility of contraction is about structure reason. You get a tree structure. And from this tree structure, there are more applications. You can build obvious routing from it. When you have a tree, it's algorithmic friendly. So it's good. But it's not our concern here. The real concern, like our main concern is about update time. And I want to say that because we contract, that is useful for update time. Why? Because if you consider a graph at level I, let's say this is a graph at level 1, level 2, level 3. With contraction, you can see that the graph size shrink because the number of edges here crossing the first expanded decomposition is 5m. So the graph in the next level literally just have 5m edges. And the next level is getting smaller and smaller. So the graph size, the higher up the graph, the smaller it is. Now I claim that actually, like when you look at the graph at level I, you actually for a technical reason, you need to recompute the expanded decomposition after 5m, 5 to the im updates. So the higher level, you need to recompute it more often. But now, because you need to recompute more often, but with contraction, the graph size also is getting smaller. So the amortized update time, when you look at like just for rebuilding, the amortized time for rebuilding only is something like the graph size over the period of time that you need to rebuild. But with contraction, the graph size and these periods are basically the same. So it's good. Without contraction, if the graph size here is big, but you rebuild it often, then the update time is bad. So this is the one utility of contraction when you don't actually care about whether it's a tree structure. You just want the graph size to be small, the higher up the hierarchy. Okay. So the point is that we need graph size reduction, even though it's not a tree. So this is something that we need. Another thing that we need is to control recourse, the recourse control per level. Let me tell you more about what is recourse. Okay. So imagine that you have this structure, the hierarchy, and there is one single batch of update, DH updates. So what can go wrong with the naive approach? So this first level here is just an expanded decomposition. And the expanded pruning algorithm that I mentioned, given the updates, the prune set, the volume of the prune set have size something like d/5. Okay, so you might prune d/5 edges from the expander. When you prune something out from expander, it means that this structure of the expander change. So this d/5 edges might need to like change, and you forward it up to the next level. So per update, it looks like the change, the number of change that you give to the next level per update is like d/5 over d. There are like you have d/5 change over all d update. So on average, the change is like 1/5 that you forward to the next level. But what does it mean when you look through the whole hierarchy? So one update gives you 1/5, which gives to the next level 1/5 square, 1/5 cube, and so on. But the number of levels is this number because you also shrink the graph by 5 factors per level. So this will just propagate and give you M, basically, meaning that one update generates so much update when you go up the hierarchy. So that's bad. So what's clear is that you cannot just manage to get the recourse, the change per level to be 1/5. You need it to be better. So the point is that this change between level or recourse here, this is what I mean by recourse. You require a lot of careful treatment here. So this challenge is there in the normal expander setting, normal expander hierarchy setting, but it's even worse in the length constraint hierarchy setting. Okay. So let's recall length constraint expander hierarchy, the picture that we saw. You have a graph, you increase the weight edge a bit, and you get router on top of it. And that gives you the next level, and you build, like you compute expanded decomposition and its witness. Okay. You see that right now, the picture that I draw, the graph size itself is not shrinking. So that's not good. So we need to take care of this. We need to take care of these two issues that I mentioned. The first, right now there is no graph size reduction. We need to reduce the size of the graph. But how, right? There is no connected component. It's not clear what to do, where to contract. So the solution that you're gonna see today is that there's a way, and we call that dynamic vertex specifier. Next is that you also need to control recourse between levels. And the recourse of dynamic, which means that between one level, you need to control the recourse of dynamic length constraint expanded decomposition. And that requires some care. Like if you want recourse to be 1/5, that's easy. That's kind of really intuitive. To go below that, you see that some technique. So next is about the dynamic expanded hierarchy, and Yahweh is gonna explain and tell you how to deal with this. So I guess should we have like maybe 5 minutes break, and then Yahweh can continue, right? Okay, then see you in 5 minutes. Yeah.